Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel.
Good day, everyone. I welcome you to the seventh episode of Christ Physics for Secondary School. And today, in this episode, we are going to be dealing with electric field. Now, these electric fields they can be best understood by their properties. The properties of an electric field, which is a region of space that is under the influence of electric force, are number one, the lines of force starts from the positive charges and end only on negative charges. The number of field lines starting or ending is proportional to the magnitude of the charge. So what this means is that the force will always travel from positive charge to negative charge and not vice versa. Next, we have that the lines of force do not cross each other. If they did, it will mean that the electric field would point in different directions at the same point. That does not make any sense. Next, we also have in a uniform field, the lines of force are straight, parallel, and uniformly spaced. Yeah, that's true. And next, we have lines of force indicate the direction of the electric field. So the field points in the direction tangential to the line of force at any point. Then we also have that the lines of force are continuous in any region with free charges. Finally, the lines of force are drawn such that the electric field is proportional to the number of lines crossing unit area perpendicular to the lines. So what this means is that the density of the lines, or the closer they are together, means that the electric field is stronger. The last time we said electric charges, unlike charges, attract. Now the difference between the charges is basically similar to what is known as potential difference. An electric charge can be at rest or in motion. So when they are at rest, we call it static electricity. When they are in motion, we call it current electricity. But the electric current is defined as the rate of flow of electric charge during a conductor. So this conductor they moves due to forces of attraction and repulsion. So when they are moving, it's called current electricity. Aside from electric current, we also have another term called potential difference. And potential difference is kind of like the slope of the electricity or the electric field, and it's defined here as it is work done in moving a positive charge of 1 coulomb from one point in the electric field to another. So that is the work done moving a unit positive charge of 1 coulomb from one point to another. That is called potential difference. Now, one dominant property of electricity is that electricity always has to flow in a loop. So that's why we have these loops here, and they are called circuit diagrams. Basically, a circle is the path traced by the electrons moving at high speed along conductors. So they pass through different pathways. Now, basically, anytime they form a closed loop, it's called a closed circuit. But anytime there's a gap in that loop, it's called an open circuit. And anytime there's no gap but it has no load, it's called the short circuit. So a short circuit is often responsible for the heating of most electrical instruments and electrical devices, because there is no the resistance of the wire is causing the electricity to heat it up, and because there's no load which is transferring the energy from electrical energy to any other form, so most of a large power is passing through a large current. So then, if you are familiar with electricity, you will have heard of the I square RT loss, which is the loss of work. So we'll talk about the work now subsequently. Now, just a moment ago, I was chatting about I square RT loss, and let's quickly talk about work. And that I square RT I mentioned earlier, we're going to be talking about it in a later section. But basically, work W is measured in joules and Q is measured in coulomb, and the EMF of a cell is measured in voltage. Hence, the voltage is equal to the work divided by the charge. So, or you can, when you make the work the subject, you can also read it as work equals to the product of the voltage and the charge. So that is W equals QV. Now this is another way of writing the work done in an electrical circuit. So and it is directly proportional to both the quantity of electricity or charge passing through the conductor and then the potential difference. So I like seeing potential difference as kind of like when you have a an inclined plane. Now potential difference is kind of like the slope of that inclined plane. So when the slope approaches a very high value, so that means the potential difference is also increasing as much as possible, and it's increasing more as the slope increases. So now let's talk about the EMF, which is also related to the potential difference. Now, but in this case, the EMF is kind of defined in terms of the potential difference. EMF stands for electromotive force, and then it is defined as the potential difference between the terminals of a cell when it is not delivering any current in an external circuit or when it is in an open circuit. So you remember the circuit we discussed earlier. So in that open circuit, when we measure the voltage between the two terminals, we get it as the EMF, because it's not supplying any current to any external load such as a lamp or a bulb. Now, electrical energy doesn't just come from its own self. It comes from different sources, and one notable source of electrical energy is from chemical energy. You can also get it from heat energy. We could get it from mechanical energy, and we would get it from solar energy. So let's talk about chemical energy. Now, chemical energy, you've probably used batteries before. Now, these batteries, they operate using chemicals. The chemical reactions between these chemicals, they can work together and it can cause different solutions called electrolytes to transfer electricity. Now, these electrolytes, they have different materials and they have high conductivities. Now, when these chemical reactions happen, they make the electrons flow because of the anions and cations in the solutions that are moving. Then there's deposition and dissolution of different substances, and as a result electrical energy flows. Now, but one thing we need to understand is that there are also defects of these cells. For example, we have what is known as polarization, because now when these anions and cations are flowing, like for example your hydrogen forms, it's called hydrogen gas, and it forms around the copper plate of a simple cell. Now basically a simple cell is a type of cell that it cannot be recharged, so it's just used once. And the example of this is Daniell cells and Leclanche cells. Now basically the hydrogen is produced by the reaction of zinc and dilute sulfuric acid. So now the sulfuric acid here is the electrolyte, and it is the liquid that conducts electricity. Then we have the zinc, which is the electrode, and copper is also the electrode. Now when we have hydrogen deposited at one of the electrodes, which is not supposed to be so, you will have a back EMF generated. It's just like a force that is opposing the force of the electrical circuit, and then that reduces the voltage at the power pole. Another way, when we are talking about electrical energy generated from heat energy, it involves the use of an instrument called a thermocouple. Now this has a cold and hot junction, and then the heat energy can be converted into electrical current by joining two different metallic wires like iron and copper, as you can see in this diagram. And then you have it, they are both connected to a galvanometer. Now a galvanometer is used to measure small currents mostly, and then you have your cold junction and your hot junction. Now basically these two different metals, they have their different conductivity, and the difference causes a potential difference. So there's a cold junction. The junction placed in the hot water is known as the hot junction. Then the end in the cold water is the cold junction. So then the difference in temperature will cause a generation of electrical current. And this heat energy is often used, but it's not very common, because most of the time you have to use energy to heat the water. But it's also another way of generating energy. You can also try it as a DIY project, and this energy is produced by the process called thermoelectric effect. So the current produced by the thermoelectric effect is very small and it can only be detected by galvanometers. So that is another reason why it is not used on the industrial scales, because the energy used on industrial scales they are very large and this one can only produce small energies. Now another way of generating electrical energy is by using solar energy, and this is what occurs when you make use of your um, the solar plates. Now these solar cells, when sunlight falls on photosensitive surfaces, the electrons are produced whose movements constitute the current. And a photoelectric cell or photocell consists of a photosensitive surface or a cathode and a wire ring as an anode. So the cathode is a photosensitive surface, and then the wire ring is the anode. So basically, if visible light falls on the surface, electrons are emitted by the photoelectric effect, and the flow of the electrons can be detected by a micrometer, now which is also used by is micrometer for measuring small currents. Now this is the diagram of a photocell. Then you have your metal cathode, which is the photosensitive surface. So it's this surface that sunlight will hit, and then it will cause a emission of electrons, and these electrons will flow to the anode, which is placed at the relatively negative potential to the cathode. So now, if that's when that occurs, the circuit is completed. There is a pushing force, which is known as the potential difference, and that causes electron to flow, and then you have electricity. So that's how solar electricity is generated on the simplest scale. So technology also improves this by making use of different materials and polymers and so on and so forth, and different ways of harnessing energy. But this is it in the simplest effect. Now, folks, this is a mock-up demonstration of how a circuit looks, and this is very close to how it looks in real life. So you have your circuit and you have your key, which is used to make or break the connections, and once your key is connected, then your electricity will flow through the circuit. It will flow through every part of the circuit, like the ammeter, resistor, voltmeter, rheostat, and other devices. Now resistance is one thing we'll be dealing with for most of this course, because resistance is a property of different and every element and every substance, because resistance is also present in everything to some degree. Now resistance is defined as the opposition to the flow of charges or currents. Its unit is the ohm. Now resistance is very simple to understand, just the opposition. It's kind of like in literal terms, it is the electrical counterpart of friction. It's kind of like electrical friction that opposes motion of electrical charges. Now basically that's for you to understand it more, for those of you who are more familiar with classical physics. Now basically, when we move on to this other concept of resistance, is also known as the unit of ohm. It has a unit of ohm. There are many ways of connecting electrical resistors, and we are dealing with two in this series, and that will be the parallel and the series connection. Now when we talk about the parallel connection, it is much different from the series connection. And let's start from the series. The series, when they are connected end to end, is known as a series connection. As in this diagram here, you can see that from one end to the other, they are like um like 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 automobiles in a traffic jam. So now basically, when they are connected like this, the equivalent resistance of the combination is given by the R, which is the equivalent resistance, equals to R1 plus R2 plus R3, and so on and so forth, if depending on the number of resistors that are connected in this way. On the other way around, there's another configuration which we could use. So that is known as the parallel configuration, and that is what is being shown in this diagram in this video. And now this arrangement is characterized by the fact that the potential difference across the resistors is the same, but the current through each resistor is different. So if you test R1, the potential difference of R1 will be the same, potential difference of R2 will be the same, potential difference of R3 will be the same. Now this is because, let's just say they are in phase, they are in the same state, so that's why they have the same potential difference, but their current is different. Now the combined or equivalent resistance is given by 1 over R equals to 1 over R1 plus 1 over R2 plus 1 over R3. So this is simply the addition of the reciprocals of the different resistors or resistance values, and then you are going to look for the reciprocal of your corresponding answer. So that will be your resistance in parallel. Next, we'll be discussing one important law and postulates that is widely used and generally accepted in electricity, and it has also been practically verified and demonstrated to be valid. Now, this is known as the Ohm's law, and this Ohm's law, it is kind of like the quadratic formula in terms of electric and electronics. So in mathematics, we have a formula known as quadratic formula, which is kind of like a very useful formula that solves all types of quadratic equations. In the area of electrical engineering and electronics, we have the formula which is Ohm's law, and it is widely used in various different applications, and it's kind of like the quadratic equation formula of electricity. And this law states that the current flowing through a metallic conductor, for example a wire, is directly proportional to the potential difference across its ends, provided that the temperature and other physical conditions of the conductor are kept constant. So what it's trying to say is that anytime you have the current will increase when the potential difference increases, provided that your temperature and other conditions are kept constant. Now, these other conditions, they could include the resistance of the conductor, the conductance of the conductor, and so on and so forth. Now, this law is what you should always remember, and it has a mathematical representation. Now, these are the statements of Ohm's law. In the first equation, you can see that the V over I equals R. Now, this R is kind of like the constant in Ohm's law. So, in Ohm's law, we are assuming that the resistance of a conductor is actually constant. But this assumption is not often correct. But because most of the time, the resistance of a conductor, it varies with the temperature, but let's assume that the resistance is constant. Then next, when we multiply through both sides by I, which is the current, we have V is equals to IR. Now, just in case you don't know, the V stands for the potential difference of that electrical circuit. The I stands for the current running through the electrical circuit wires. Then the R is the resistance of that total electrical circuit. So at times you can differentiate resistance into external and internal resistance. So it depends on the conditions. We'll be talking about that in a separate episode of this video. Now, the reason why the resistance of a conductor, and indeed any conductor, is not often constant is because of the fact that resistance, as this equation shows, is directly proportional to the length of the conductor and inversely proportional to the area. And now that rho is called the constant of proportionality, and that constant is also known as resistivity. So resistance is equal to the product of the resistivity and the length divided by the area. So you can see that a longer metal we have a greater resistance, and then a metal with a wider area we have a smaller resistance. So there's a direct proportion between length and the inverse proportion between area. That's for resistance. Now let's talk about finally the concept of power. Now the concept of power is a very important concept because it's discussed every day in our everyday life, in real life, because most of the time we use power in our electric devices, in our cars, not just in electrical devices, just in most machines. They talk about the concept of power. Now, this concept of power is very important for us to understand, and it is defined as the rate of doing work. Now, that means that power is equal to the work done divided by time. So power is equals to work divided by time, but in this case our work is equals to IVT. So that is work is the product of the current, the voltage, and the time taken for that current to pass through. So that means in this case our power will be equals to IVT over T. That will be IV, and then that will be V square over R. The reason for that is that I itself is V over R, so that's V over R times V, that's V square over R. Then you can also change it to when V square over R, because that R itself is equals to or rather V itself is equals to IR, that's IR times IR over R, that's I square R. So there are different ways you can express power. These are different formulas, equations here, and power is what I will leave you with today for this video, and I hope you've been able to gain something about the basic concept of electricity. And I'll see you next episode. There we'll be talking about something further than this. For next episode,
we'll be talking about the topic of particulate nature of matter.